Okay, well, let's get started. Okay, for those of people who are eavesdropping here, this is the second pilot in our experiment of doing Wolfram Language design reviews live streamed. So today we are talking about design for chemistry in Wolfram Language, and we're just doing what we do every day, trying to do what I've been doing for like 30 years now, making coherent and unified designs for Wolfram Language. So let's see how we manage to do on chemistry. All right, let's get going. Okay, let's get to work. All right, so let's see, what we're looking at here is this wrapper that we're calling molecule, which, does any of this actually run?
Not in the kernel right now, but in my package, everything in there would evaluate.
Well, should we do you want to give me a version that will actually run, or should we see your screen, or should I just look at what you've got here?
Well, so I can, so I could share my screen to do a quick demo, but
okay,
I'm not.
I mean,
didn't prepare.
basically, okay, all right, fine. So let's just understand what the basic point is. There are various kinds of input for this molecule thing, and the main thing, what is that graph? Is that an ordinary graph, or is that
right? That is an ordinary graph. I haven't, so we haven't nailed down the design on that. You mentioned wanting to be able to give it a graph and assume everything
assume carbons.
Is right.
Is that right?
Right, okay. Or perhaps be a little bit more intelligent and look at that and try and put in hydrogens where they might be.
I see. Is that plausible? Or I see, but so in other words, the graph will be a carbon backbone of some kind, and then it's like, okay, where would the hydrogens go? Is that the idea? Right. Ions of some kind, or that's what this is here.
The biggest difference is not their exit. The difference is that they're indistinguishable.
What do you mean by that comment? I mean,
like in a graph, there's always one vertex is never the same as itself trivially, where two carbon atoms that have the same neutron number are the same from a quantum mechanical point of view.
That is certainly true, but they appear in different places. So what for us?
Well, so for
kind of implicit permutation symmetry.
Yeah. Okay.
So from a language point of view, though, the big difference there is that in graph, the list of vertices needs to be let's see, if you run delete duplicates on the list of vertices, it should have no effect. You should not have any duplicated vertices. But with a molecule, that is not the case. And so in a graph, you lay out your vertices. You can give them any arbitrary Wolfram language expression. The easiest thing to do is to give them
as their name. Right. Okay. But so here, you're not naming the vertices at all. Here, you're just having sequential indices for the vertices. And I mean, in principle, we could allow names for the vertices. I mean, that's the same type of issue that we have in, for example, neural nets, where we have the notion of a net chain where we just have indices, or a net chain, I think, can also take an association, can't it? Where it's actually naming the different layers and so on. So similarly here, in principle, we could.
And then you do bookkeeping, and you would find, you would assign formal charges in that way.
So for example, if I have a sodium chloride thingy, right, which with what little chemistry I know, I think, does that have would that say Na with a +1 here, or what?
Right. And then so that's a disconnected ion, and you can also have charges within a molecule. Like if you look at TNT, your nitro group, you might have a positive charge on one nitrogen, a negative charge on another oxygen. And this is, we say it's the formal charge because in reality, the electron density
and the partial charges are used for that aspect of the modeling and modeling the energy.
Okay, so all right, so there's probably some other thing that we're going to need to include here, but let me understand some other things. So this 6 could equally well be carbon as an entity, is that correct?
Yes.
That or the string C, capital C, the atomic symbol.
Yeah, right.
So, okay. I mean, along the entity line, one thing that would work there would be an entity instance of the atom carbon, or of the element carbon, with a formal charge and an isotope and
Right, that is a reasonable thing. I mean, okay, so that's an alternative to this association here.
Right.
Right. So, I mean, now let me point out in this association, this -1, you should also at least support, electron charge as a unit there, right?
Right. Yes.
And, with isotope, is that the right name for that? Where you say isotope? I mean, that's really, I mean, unfortunately, it's not the atomic mass. Would you?
So another option would be what we use in chemical data is non-standard isotope number.
The heck does that mean? What do you mean non-standard? What is it? The words non-standard isotope number?
Right.
That's
yeah.
crazy. I mean, what is there a notion of an isotope number or what?
It's the mass number. I think,
okay,
right?
it's usually called mass number.
Is that right, Bob?
I believe so. We generally
the protons plus neutrons number.
Exactly.
Right.
Exactly. The number of nucleons.
Yeah, well, let's not call it nucleon.
No, but.
Okay, so mass number. Yeah, that's the number A. Fine. So, I mean, unfortunately, if somebody actually sees this, they will be confused if it doesn't say, I mean, it might need to say isotopic mass number or something, which is very long, but it doesn't really matter how long it is.
That I think would be good because in chemistry applications, it's carbon 13 that's important or carbon 12 when you're dealing with atomic structures and things like that. You're not worried about the natural abundance.
Yeah. Right. I mean, you actually want right, but I mean, this is okay. But the next question is this. I am not a big believer in this really wacky property thing. But let's keep going on these other. So we're talking now about the entities, and we're saying there are a variety of forms that they can be given in, including potentially an entity instance or this association. Is that the idea?
Right. And I don't know if you want to talk about this now, but that did bring up the point of to what degree do we need to match the syntax or the names of properties from chemical data where there is a precedence, whereas if in the molecule.
Which, like what?
So like in chemical data, there's non-standard isotope numbers. There's.
We should probably change that. I mean, we should probably also provide a different name for that.
And let's see, so atom positions and vertex coordinates to distinguish between 2D and 3D in chemical data. Whereas I believe Bob would really prefer, coordinates might just seem more natural than atom positions.
What do we call it in chemical data?
Atom positions in contrast to vertex coordinates. So those two names don't tell you that one is 3D and one is 2D until you look at the.
That's kind of stupid. Yeah, it's kind of stupid. So you're proposing something like atom coordinates or something.
Right. And then we would.
And what's this list of formal charges? How does that work in chemical data?
So it'll be a list of integers as long as the list of atoms.
And where's the list of atoms? The list of atoms is
vertex types.
That's horrifying.
Right. It's a real hodgepodge of graph nomenclature and chemistry.
Right. Okay. Well, so we need to fix that. I mean, it's not really a huge problem because we can keep supporting the old names, but we just have to. All right. So which ones of these have you got a list of which ones need to be rethought here?
No.
Okay.
We don't have such.
Okay. All right. Let's this molecule thing. Do we really want to use the name molecule, the actual, as opposed to molecule object or some such other thing? Molecule entity, molecule. What are we calling this? Didn't we have another name for this before?
We were doing a molecular structure. We started chemical structure and then we moved to molecular structure. And
I think that's better. Why would that?
Okay.
What's wrong with that?
I just like the way that molecule rolled off the tongue. Is why I.
Well, it's a cool thing, but I'm just concerned. I don't know. First of all, is it always a molecule?
No. So sometimes if it has a charge,
yeah,
it's not technically a molecule by IUPAC standards. And if if it's a disconnected structure, it's not technically a molecule by IUPAC standards.
All right, but okay, but let's take a look at these things. So this bond, so this thing here will be presumably equivalent to one, an undirected edge in a graph, yes?
Yes.
Okay, but you've got to annotate this. Now, Roger, I think that you've been wanting to annotate edges on graphs for a while, right? Roger?
I was on mute. I mean, we do. That's what property is for. So they have an open-ended set of annotations.
Well, so you can do that, right? I hate this name, property. We really should come up with a better name.
Yeah, it should be attribute. But someone, yeah.
But that was taken 30 years ago.
Exactly, for something completely marginal.
I don't know how marginal it is, but okay. In any case, let's.
But yeah, so now, but besides that, there is an open-ended set. You can add however many that you want. Okay, so if you have a meaning to double, for instance, or there might be some other kind of, edge. They mean very different things depending on what it is that you model.
Okay, but so if I have an edge, I can have a list of name value pairs. Is that right?
Yeah.
Okay, but so what would you do in the case of double? Would you say double arrow true, or what would you say? Double bond arrow true?
No, so you would say bond order goes to double, or yeah.
Okay.
Because there are different.
Is that what it's called? Bond order? That's really confusing. I mean, especially when you've got a counterclockwise running around.
No, bond order is the accepted term for the multiplicity of a covalent bond between two atoms.
But you just use the word multiplicity as well. Is that an alternative?
You could say bond multiplicity.
So what for us?
Well, so for
implicit permutation symmetry.
Yeah. Okay.
So from a language point of view, though, the big difference there is that in graph, the list of vertices needs to be let's say if you run delete duplicates on the list of vertices, it should have no effect. You should not have any duplicated vertices. But with a molecule, that is not the case. And so in a graph, you lay out your vertices. You can give them any arbitrary Wolfram language expression. The easiest thing to do is to give them
as their name. Right. Okay. But so here, you're not naming the vertices at all. Here, you're just having sequential indices for the vertices. And in principle, we could allow names for the vertices. I mean, that's the same type of issue that we have in, for example, neural nets, where we have the notion of a net chain where we just have indices, or a net chain, I think, can also take an association, can't it? Where it's actually naming the different layers and so on. So similarly here, in principle, we could name the atoms. Would we ever want to?
Well, I think you might want to have a tag for the atom. Bob has extensive experience in molecular modeling, and you might want to keep track of the molecule, an atom, from one transformation to another.
Right. Often that's the case. It's much more convenient to refer to an atom by a name that you've given it or that's been assigned, rather than trying to always count and where does it fall, because when when you edit a molecule, the position can change.
But so there's two ways we could imagine doing that. One is the whole thing turns into an association and everybody has a name, and those names could be sequential integers, or they could be names like Jim or something. But here, I mean, what you're saying here is that otherwise an atom is specified by its atomic number. That's the generic way to specify it. What is the formal charge? Is that an ionization thingy, or what is that?
Yes, it's not it is an ionization state. It's not technically the charge that would be there. It's if you took all of the charges of a bond and split them evenly, all the electrons of a bond, and you split them evenly, and then you do bookkeeping, and you would find you would assign formal charges in that way. So
for example, if I have a sodium chloride thingy, right, which with what little chemistry I know, I think does that have would that say Na with a +1 here, or what?
Right. And then, so that's a disconnected ion, and you can also have charges within a molecule. Like if you look at TNT, your nitro group, you might have a positive charge on one nitrogen, a negative charge on another oxygen. And this is, we say it's the formal charge because in reality, the electron density might redistribute these charges in a way that's not as entirely localized as we would say for a drawing or for bookkeeping purposes. But it's a useful tool for representing the molecule. It's not necessarily indicative of what the actual charge.
Molecular modeling in the past, the formal charges are used merely for bookkeeping on valence, and partial charges are kept for the actual partial charge for some Coulombic calculation, for example.
Sorry, I missed a few words there because the audio dropped out for some reason. Are you saying there's a different thing than formal charge? There's something else called partial charge?
Yes, in molecular modeling. Yes, in molecular modeling, partial charges are used for the redistributed whole molecular charge. The sum should still be 0 for a neutral molecule. But for example, nitrogens and oxygens tend to have more charge around them than carbon or hydrogen do. And it's important for docking studies, for example, when you're trying to dock an inhibitor into a receptor site or something like that, because they interact with the surrounding protein structure. And the partial charges are used for that aspect of the modeling and modeling the energy.
Okay, so all right, so there's probably some other thing that we're going to need to include here, but let me understand some other things. So this 6 could equally well be carbon as an entity, is that correct?
Yes.
That or the string C, capital C, the atomic symbol.
Yeah, right.
So, okay. I mean, along the entity line, one thing that would work there would be an entity instance of the atom carbon, or of the element carbon, with a formal charge and an isotope and
right. That is a reasonable thing. I mean, okay. So that's an alternative to this association here.
Right.
Right. So, I mean, now let me point out in this association, this -1, you should also at least support, electron charge as a unit there, right?
Right. Yes.
And, with isotope, is that the right name for that? Where you say isotope? I mean, that's really, I mean, unfortunately, it's not the atomic mass. Would you?
So another option would be what we use in chemical data is non-standard isotope number.
The heck does that mean? What do you mean non-standard? What is it? The words non-standard isotope number?
Right.
That's crazy. I mean, what is there a notion of an isotope number or what?
It's the mass number. I think,
okay,
right?
It's usually called mass number.
Is that right, Bob?
I believe so. We generally
the protons plus neutrons number.
Exactly.
Right.
Exactly. The number of nucleons.
Yeah, well, let's not call it nucleon.
No, but.
Okay, so mass number. Yeah, that's the number A. Fine. So, I mean, unfortunately, if somebody actually sees this, they will be confused if it doesn't say, I mean, it might need to say isotopic mass number or something, which is very long, but it doesn't really matter how long it is.
That I think would be good because in chemistry applications, it's carbon 13 that's important or carbon 12 when you're dealing with atomic structures and things like that. You're not worried about the natural abundance.
Yeah. Right. I mean, you actually want right, but I mean, this is okay. But the next question is this. I am not a big believer in this really wacky property thing. But let's keep going on these other. So we're talking now about the entities, and we're saying there are a variety of forms that they can be given in, including potentially an entity instance or this association. Is that the idea?
Right. And I don't know if you want to talk about this now, but that did bring up the point of to what degree do we need to match the syntax or the names of properties from chemical data where there is a precedence, whereas if in the molecule.
Which, like what?
So like in chemical data, there's non-standard isotope numbers. There's
we should probably change that. I mean, we should probably also provide a different name for that.
And let's see, so atom positions and vertex coordinates to distinguish between 2D and 3D in chemical data. Whereas I believe Bob would really prefer, coordinates might just seem more natural than atom positions.
What do we call it in chemical data?
Atom positions in contrast to vertex coordinates. So those two names don't tell you that one is 3D and one is 2D until you look at the...
That's kind of stupid. Yeah, it's kind of stupid. So you're proposing something like atom coordinates or something.
Right. And then we would...
And what's this list of formal charges? How does that work in chemical data?
So it'll be a list of integers as long as the list of atoms.
And where's the list of atoms? The list of atoms is...
vertex types.
That's horrifying.
Right. It's a real hodgepodge of graph nomenclature and chemistry.
Right. Okay, well, so we need to fix that. I mean, it's not really a huge problem because we can keep supporting the old names, but we just have to... all right, so which ones of these, have you got a list of which ones need to be rethought here?
No,
okay,
we don't have such.
Okay, all right, let's do this molecule thing. Do we really want to use the name molecule, the actual, as opposed to molecule object or some such other thing? Molecule entity, molecule, what are we calling this? Didn't we have another name for this before?
We were doing a molecular structure. We started chemical structure and then we moved to molecular structure. And
I think that's better. Why would that?
Okay.
What's wrong with that?
I just like the way that molecule rolled off the tongue. Is why I.
Well, it's a cool thing, but I'm just concerned. I don't know. First of all, is it always a molecule? No.
So sometimes if it has a charge, it's not technically a molecule by IUPAC standards, and if it's a disconnected structure, it's not technically a molecule by IUPAC standards.
All right, but let's take a look at these things. So this bond, so this thing here will be presumably equivalent to one, an undirected edge in a graph, yes?
Yes.
Okay, but you've got to annotate this. Now, Roger, I think that you've been wanting to annotate edges on graphs for a while, right? Roger?
I was on mute. I mean, we do. That's what property is for. So they have an open-ended set of annotations.
Well, so you can do that, right? I hate this name property. We really should come up with a better name.
Yeah, it should be attribute. But someone, yeah.
But that was taken 30 years ago.
Exactly, for something completely marginal.
I don't know how marginal it is, but okay. In any case, let's.
But yeah, so now, but besides that, there is an open-ended set. You can add however many that you want. Okay, so if you have a meaning to double, for instance, or there might be some other kind of, edge. They mean very different things depending on what it is that you model.
Okay, but so if I have an edge, I can have a list of name value pairs. Is that right?
Yeah.
Okay, but so what would you do in the case of double? Would you say double arrow true, or what would you say? Double bond arrow true?
No, so you would say bond order goes to double, or yeah.
Okay.
Because there are different.
Order? Is that what it's called? Bond order? That's really confusing. I mean, especially when you've got a counterclockwise running around.
No, bond order is the accepted term for the multiplicity of a covalent bond between two atoms.
But you just use the word multiplicity as well. Is that an alternative?
You could say bond multiplicity.
That sounds much better to me than bond order, which sounds like it's,
Yes, especially when we use order to mean the order in which things occur in a list, which we do all over the place.
So I would go for bond type instead of bond multiplicity, because
It's more forgiving and we can abuse it more. Also, I was just thinking for the whole thing itself, instead of molecular structure, how about molecular model? Because we're really talking about models.
That's an interesting name. That's an interesting name. And how does that agree with, I mean, molecular model or molecule model sort of agrees with our system model concept.
I guess I feel like everything is inherently a model. Like,
yeah.
So when you make a graph, it is a model of a graph.
It is.
Yep. I mean, what do you mean it's a model of a graph? It's a graph is an abstract thing.
Okay.
Yeah, but
a mesh region.
No, but we have. But this realization is coming slowly to everybody, and it will be more by year. You know, so distribution is a model, but we call it distribution.
Well, it depends what you mean by a model. Look, there is a perfectly Platonic abstract concept of a distribution that has nothing to do whether the distribution has anything to do with the real world. That's where modeling comes in. But as an abstract kind of thing,
it is a model.
What do you mean?
No.
A Gaussian is just a Platonic thing out there in the abstract formal world.
Like the modern view what a physical theory is. A physical theory is a set of mathematical axioms and a corresponds table to the reality. And only with this corresponds table, something becomes a model.
No.
Well,
so in statistics, the notion of model is different. You know, a model is something that's usually a mechanism that can reproduce the aspect that you're interested in modeling.
That's true.
Same goes for system modeler.
Yeah.
It's not precise. You know, you can always build a more precise.
I think we all agree that's what a model is. The issue, which we should.
But it has, you know, this. Yeah.
Right, but the issue is, look, are integers just an abstract thing, or are they, when you have the integer 2, is it the abstract integer 2, or is it a model of the integer 2? I think one would normally consider it to be the abstract integer 2. Now, it's a separate, getting into model theory and
modulo logical analysis.
Yes. Modulo the non-standard arithmetic and all this kind of nonsense. But so the point here is that one could imagine. Okay, so let's imagine that somebody was actually doing an experiment, was actually using, So there's an interesting question. Let's say that. So Roger, in the case
just for your example, okay. So some systems and whatnot and books, they don't call things distribution; they call them models. That's
maybe
it.
So, but
Gaussian model and so on.
Yeah, I'm aware. I'm aware.
So
right, I know.
That is a model. It is a model.
Okay, that's a use of the word model. It's a slight abuse of the word model, as in a model is something which makes a connection between formal abstract world and the concrete world of things that exist in physical reality. Anyway, let's not go deep philosophical on this. I personally think molecular model or molecule model is an interesting potential name for this. But let's continue. Go ahead.
It's a decent name.
You agree it's a decent name?
Yeah.
Okay, fine. Okay, so we didn't actually. So that philosophy discussion was irrelevant. Is that true, or is that?
Yeah.
Okay, fine. Just checking. Okay, so should it be molecular or molecule model? Molecular model sounds better probably, although it has a certain resonance with those things made of wood and sticks and so on.
But it's not too dissimilar.
Exactly.
Okay, fair enough. Okay, all right. What is a chiral center? What is that?
It is an atom that has 4 distinct ligands attached to it, and they appear in a particular order that give it a handedness, either right-handed or left-handed. They're not superimposable, but the mirror images are superimposable.
And how many more graph theory? I mean, so what you're doing there is you're specifying an aspect of the graph that is beyond, in a sense, you're specifying not just the connectivity of the graph, but some topological data about the system.
Yes, and it's related to the 3-dimensional structure, and it's extremely important in biology and pharmaceutical sciences.
Okay, but so just so I understand, what I mean, what other topological constraints get put in? I mean, obviously, at some level, ultimately, you're going to say this molecule has its atoms at these positions, and then you can get even more detailed than that. But what other kind of gross topological constraints or topological, what other gross topological information is there that you have to specify in setting up the?
I think this is about it. I mean, there are also chiral axes and chiral planes. We don't need to worry about those too much, especially not for the first cut.
Yeah, but what will they look like? How many atoms? So in a chiral plane or something.
A chiral plane has to do generally with rings and one side being different from the other, and not just a matter of flipping it over in 3 space. Chiral axes are related to a chiral center, except it's not around a single atom. Generally, it's around a series of double bonds or from one.
Okay, but so how would we specify that? So in this chiral center thingy, I'm sorry, chiral. What were you saying? Chiral
center.
No. The last.
Oh, chiral axis. Again, it's 4 ligands around a core of atoms.
Okay, so instead of a single atom here, you might have some list of atoms there.
Yes.
And then you would be saying.
And then you have ligands attached to it, and you have to specify those ligands and the order in which they appear in space.
Right. So those are 2 examples of the hyperedge, the multiple vertices that come together to have a particular.
Okay, so let me ask a question about graphs, Roger. So this is a case. I mean, this notion of ordering the edges that come into a vertex. Have we handled that in the case of graphs or not?
No, they're not ordered. You know, I know you want that for the tree because our expression trees are ordered trees.
Right, but so do we have a solution for that in the case of trees?
There is a solution in the sense that it's completely specified by what it's connected to.
Stephen, the distinction here that we're trying to make with a chiral center is that it's a connection between a 2D topological representation of a molecule and its 3-dimensional shape. And it's very important. If you have the atomic coordinates, there's no issue. But if you don't have the coordinates and you need to make the distinction between left and right-handed forms, this is the way somebody would do it in a database of chemical structures for cheminformatics, for example.
Okay, but fine, I get it. But so my question for Roger is, I mean, actually for my, universe models and other things, I'm interested in graphs where there is an ordering to the, connections to a vertex, right? Do we have a plan, Roger, for how we represent any of that stuff in graph?
Not really. I mean, one could make one, but it hasn't come up as a. I mean, your universe model is not a big application domain.
Well, not yet. So, the universe is big, but
right. But I mean, seriously, it sort of, if you look at it as graphs, it doesn't make a lot of sense. One can still do it because you can sort of model it with some property that each of the edges out has.
So wait a minute, what characteristic of a tree? I mean, trees do naturally have ordering on the edges that come out of a node, right? I mean,
what kind of trees are you talking about now?
Well, expression trees, for example, certainly have.
Yeah, no, I mean, no, a tree it doesn't have ordering. You can have ordered trees.
Okay, but so in what sense? All right, so we've got ordered trees, but is there a notion of ordering on a general graph that is like that? Is there a notion of ordered graphs that is the analog of ordered trees?
Not that I'm aware of.
Okay. I mean, is that a notion? What would it look like? I mean, is that a consistent notion, or is it even a nonsense notion to begin with? So around every.
I mean, one could do what I described, that you can give an additional property to each edge that's connected to it.
Yes.
A number, so you get this other property.
So you can choose to then order by that number just by looking at the labeling on the edges. Right, and you might
But it would be another property.
Right, but if you do, for example, graph isomorphism or some other thing like that, or even, I mean, it may not be consistent. It may be that if you do graph transformations of various kinds, that these orderings can't be made consistent, that there are only certain operations that will preserve, for a tree, it seems fairly easy to imagine that, gluing and chopping off and gluing on subtrees will allow you to preserve ordering. That's less obvious to me for graphs. Is it obvious?
It depends on what ultimate properties you want them to have. But you can, I see your consistency.
Right. But so the thing
there can be two numbers for each, they can be ordered locally from the point of view of every vertex, and that's basically, it says from this vertex, these are the ordering, the order everything coming out.
So that's similar to how this type of property is handled in the underlying library that we use for the molecule. So in the example right there on the page, the atom that has index 4 actually just has a property that is the CIP, the chirality, we'll call it, the direction, the handedness, and it says counterclockwise. Okay. And then you look at the bond list, and you see that it's bonded to atoms 2, 5, 6, and 7 in that order, and then from that you can know.
But this counterclockwise thing, this is, I mean, we are choosing in this particular case to say, I don't even understand what counterclockwise could possibly mean here.
So what it means.
Go ahead.
Okay, so atom number 4 is bonded to atoms 2, 5, 6, and 7.
Yep.
If you look along the axis from atom 2 to atom 4, the remaining ligands 5, 6, and 7 are in a counterclockwise direction.
Oh gosh.
It's because the carbon atom is tetrahedral in three-dimensional space.
Yeah, I understand that, but okay, but so counterclockwise means, what does it mean? It means if you put circular polarized light through it, it will rotate to the left.
No, it means going from the atoms from 5 to 7 to 1, or whatever the order is for the example, 5, 6, 7.
Yeah.
It means you're tracing a clockwise direction or a counterclockwise direction around that circle.
Okay.
And so that's
these are the rules that the chemists came up with back in the 1950s to have a nomenclature for the handedness of the molecules.
So when something is said to be a left-handed, whatever, does that immediately translate to that saying counterclockwise or saying clockwise or something?
Precisely. And the ligands, the atoms, get a priority assigned to them based on what they're attached to further out in the molecule. There's a whole graph theoretical basis for this and set of rules for disambiguating the ligands. If you can disambiguate them by these rules into 4 different ligands, then you can do the clockwise, counterclockwise, and then give it a symbol R or S for that direction.
And so the distinction there is that there's an absolute handedness to any chiral center, and then there's a local specification of it. So in the molecule expression that we have, you specify locally what the handedness, the parity around that center is, but then the global handedness is a computed property where you have to look at each thing that's attached to it, assign a number, and then decide which order those numbers fall in.
Right, because you can make a change remotely in the molecule and it will change the priority assigned to 2 ligands. So that's why we have to do it locally here with clockwise and counterclockwise, but chemists have to use a global representation, which can be computed from the structure.
By the way, do you guys think this is the right ordering of, at a trivial level, I would have thought a better thing to do would be, but maybe I'm wrong, is to have it by default look like this and default it to either clockwise or counterclockwise, or is there no obvious default?
We could say that we always express it in the clockwise order.
Is that a sensible default, or is that like a totally random? Why would you choose it default? Unclear. By the way, I also think we don't want to capitalize the C for counterclockwise, but that's a minor, very minor issue. Do we have a convention elsewhere for when things are clockwise versus counterclockwise? I mean, clearly, when we're having coordinates around a circle, for example, those are counterclockwise coordinates typically, right?
Because we're following the mathematical precedence in the plane, yes.
Right, but do we have other cases where we're also doing that? Roger, are there cases in region and mesh specifications where this comes up?
No, but our polygons in the graphics, in the 3D graphics language has, when you need to speak about, so generally speaking.
Normals, so which way the polygon normals assume?
Right, but you can speak of orientation of any set, any geometric set. We don't do that. Like our rectangle is not ordered.
Yes.
Okay. But our polygons are, because we have different, we allow different colors on the two sides, so we need to be able to say which.
Right. So what's the answer?
So for the chiral center, I would be opposed to having a default, because you could, if you didn't put a string there, which, by the way, I do like the string last as opposed to in the middle the way I have it there. But if you didn't put something there, you're specifying that we don't know the information, and that's a thing. You can have a mixture of molecules where the handedness isn't decided, or you can write out the molecule and just not know.
But then why do you need to specify this chiral center if you're not specifying the orientation?
Because sometimes you specifically do. If you look on PubChem, you'll find oftentimes for any molecule, you might find 3 distinct pages for it. One with counterclockwise, one with clockwise, and one for an unspecified mixture.
But when you say unspecified, why do you need to bother in the molecule model to actually give the chiral center specification? Why don't you just leave it out?
Right.
That's what we would do.
That's what we are doing. That would be, if you didn't give a direction, I would think that you would assume that it was unknown.
Exactly. I would.
Okay, fine. So So the basic point is there's no default. Okay, let's go on and take a look at some of these other things, and then we'll loop back to the underlying discussion. Okay, so this is where we start going crazy.
Right.
Okay, so Roger, these are the analogs of graph add, right?
Okay.
For molecules. So I have no sense. There isn't a graph add. What is it called?
So there's vertex add, edge add.
Edge add.
Is this really what, I mean, when do you, do you, we're seeing a lot of background noise there. I don't understand what these incremental things about adding and deleting atoms and bonds and so on, is that a common operation?
Very much so, especially in the molecular modeling area, drug design.
Why? I mean, it's hardly easy to do in physical practice, right? It's a whole. Okay, go ahead. Explain.
Okay, yes, it's separate from chemical synthesis. You have a drug. You've got a drug candidate, and it docks fairly well in the receptor site that you're trying to inhibit. And you see that there's some space nearby that you want to fill up. So you want to use a larger group instead of the methyl group that's there, or if it's just a hydrogen, you might want to replace it with a methyl group or an ethyl group. So you will want to add an atom or replace an atom without having to recreate your structure from scratch and going through the whole process of generating coordinates that you hope will still fit. Most of the algorithms that generate coordinates de novo do it in a somewhat ad hoc way. And as I was telling Jason just the other day, 3-dimensional coordinates for molecules, molecular models, are generally hard won, and modelers do not want to give them up. Throw them away and recreate a structure from scratch just to change a carbon to a chlorine or something like that.
Okay, but so why is it that we're not letting people, I mean, this bothers me. I mean, especially the description you just gave is not about adding an atom. By the way, whoever's not on mute and making background noise, could you try to?
So what doesn't make sense, Stephen?
You were just explaining that you would take a single hydrogen and replace it with some methyl group or something. That's not an atom add. the name doesn't make sense.
No, okay, no, that's not. That would be a fragment add or something like that specifically. But one could change an atom and then add hydrogens to fill in the vacant valencies.
Right, but what you're saying is basically you want a subgraph. You want to replace a subgraph, basically. That's the basic operation you're talking about.
Yes, in the general case, that's exactly what's going on. And granted, I'm coming from a lot of background, historical way that we used to do it in molecular modeling 30 years ago, and so on. So a lot.
Well, has anything changed? I mean,
to some extent, yes, and a lot of things have not. There's a lot of history, a lot of cultural baggage in the way things have been named and operations have been designed.
Okay, but the basic point is that you're saying that it's like, for example, if I do a graph, I mean, what we haven't done in the case of graphs, if I just make a random graph, you know, and it has a certain layout, and then I do a vertex, then I modify a vertex. What we are doing in traditional graph is completely relaying out the graph with the new vertex configuration, right? So Roger, don't we have coming a thing where you can lock some of the vertices in the graph?
Yes.
In terms of their position, how does that
just
work?
For layout purposes.
I understand, but that's what these guys care about too, because the layout is the physics.
Sure.
Exactly.
Okay. So how does it? What is our actual language design for locking the vertices?
So I can't remember 100% right now because I want to see it sort of. It's not actually operating as we speak. So, but the idea is that you can have vertex coordinates, and you can, you know, if you want to lock something, you specify the things that you want to lock, or the other way around. You know, I think we need both ways. You know.
Right, but I think we had a design for this, and I don't remember what it is. Is it just that you give a partial list of vertex coordinates? And
yeah, but you need to say which ones right now. But, you know, you need to say which ones it is that you give.
Yeah, I understand that. So it's an association of some kind.
Right. That's what I was saying, that you can either lock things down or you can say change only these. So I think both are interesting. Because sometimes, you know, often one is bigger and one is smaller, and you want to use the smaller as a convenient.
Yeah. Right. Fair enough. Okay. So there's some design we'll have to do on that. But so the chemistry case, what we're really talking about is a subgraph is getting replaced. Now, unfortunately, our subgraphs are not exactly named in the chemistry case. Atomic number.
You faded. Hello?
Hello, can you hear me?
Yep.
Yes, we can. You were saying in the chemistry case, and then you faded out.
Oh, dear. Okay. Okay, so my question is, how are you specifying an atom add where on the molecule you're supposed to be adding this?
Well, what we would do is when we did it, well, most things these days are done through a graphical interface. But before we had those, and we had a command line interface, we would say add atom, and we would give the molecules the argument. We would tell it what kind of atom we were adding, and
yeah, but I want to know where
it was attached.
So I'm sorry. What was the where? Is it a numbered atom? It's an atom number of some kind.
Depending on the modeling system you were using, it was either the atom index, or in the more recent ones, the name assigned to the atom.
Okay, fine. But as we just said, we don't have that in our case.
So that, that's a good reason to actually have individual names for them if you want to.
Exactly. That's why we went to atom names later on, because it was just much more convenient, especially in protein structures. You could name it by residue and then the standard name, C alpha, CO, N1.
So in this case, though, I feel like atom add acts exactly like vertex add. It adds the atom, but it doesn't create a bond. And then when you want to go and make a bond, you do bond add and you give the molecule, and then you give two indices.
It's really low level. I mean, doesn't it?
Yes.
I mean, isn't
That's too low level. Chemists combine all of that into one step. So you need to include the name of the atom to which you're adding it, so the bond can be made. And the default would be a single.
No, we don't have it. But the problem, Bob, is we don't, in the current design, And as Michael was explaining, quantum mechanics tells us all the atoms are identical. We don't actually have names for these atoms.
No, but we need to do something about them. Either we have to give them names or we have to do everything by index. And as Roger said, names would be much more convenient.
Well, it depends
I can imagine that there are sort of, sites that are particularly interesting to have names.
Yes.
Sure. They're like landmarks. It's like sometimes all cities are equivalent, but some of them have names.
Right. So you can have a substructure defined by a pattern, and how exactly to enter that into the Wolfram language is something I'm really interested in figuring out, but we haven't.
Okay, but fine. So
fully.
But so this is the same thing as with neural nets and so on, that sometimes the ports are just specified by indices and sometimes there are actual names assigned to them. And we've done that typically by having, in this case, what we can imagine is that the association or the entity instance could have a name that's associated along with these other things, like, well, not with bonds, but we could just have a name there that was part of the, so we could have two alternatives. We could either have an association for the whole thing, in which case everything has a name, or we could just give this particular element of that list of vertices, i.e. atoms, and have a name as part of that. Does that make sense?
Right, so to have a name key in that key value pair.
Yeah, right, along with formal charge and so on. So that means the vast majority of atoms will not be named, but a few will be, and those will be the ones that you actually will.
And you can refer to them by that name.
Right,
yeah.
But that's.
But I could see, here's another, when you do that, you can probably get a bunch of other benefits. Like someone gives you a molecule and highlights some sites. That might be interesting.
Yeah, that's a good point.
If they have a name, maybe you want to see the label for that name when you plot them, and you visualize them.
Yeah, well, that's a good point. It's highlighting of these chemical structures. Is that something that, in the case of graphs, how does the highlighting thing work? So you would say highlight graph of that graph, comma, and then what? I just give some vertex numbers like that?
That would work.
Okay. And what if I want to give a bond? Or
an edge. Then you give edges there instead of vertices.
Okay, but so I want to say, for example, the edge 2 arrow, I don't know what it's connected to, blank. Would that work?
Yeah.
How did that work? Did that do something to an edge?
No.
Well, it was taking the highlighted graph.
Oh.
No, but the highlighted graph is okay. The highlighted graph is just a graph.
Yeah.
No, but that's what you took as input. So I'm not sure it actually.
No. Highlight graph is just a graph.
Yeah.
No
okay.
Which is good, and that's the same thing that should happen for. So you're doing that with property wrappers in the graph. Is that correct, Roger?
That's correct.
So we should either use the same mechanism or a very similar mechanism in the case of molecules, because we're definitely going to want some kind of highlighting mechanism in the case of the molecules.
Yep.
But, so now, in the case of a graph, do we have subgraph replacement yet?
No.
Right. So subgraph. In principle, I might say this subgraph involving these three vertices gets replaced by this other subgraph, right?
You can pick it out. If you want the various.
So go ahead. Tell me the subgraph that is associated with vertex number 3 or something. How do I get that out of this
subgraph? Amazingly.
Okay. What do I say? Comma 3?
Yeah, you can say a bunch of vertices.
Or you could do an edge, right? 3 goes to blank.
Yeah, but that's not a very exciting subgraph. I want to know what's connected.
Yeah,
how do I get the dangling legs of
well, pick some more vertices.
Oh, but how do you find the ones that are
connected to 3?
First neighbors to 3.
Neighborhood graph.
Okay, so if I say of this thing, neighborhood graph of %3, comma 3.
Yeah.
Okay. And can I go 2 levels out or something here?
Yeah. I can't remember the argument, but
there we go. Yep. Cool.
Wonderful intuition.
So if I say vertex labels arrow automatic here.
Mm-hmm.
Very cool. Okay. All right. So that's the kind of thing that we want to have. Okay. So what would be the analog of neighborhood graph? Is that the relevant thing? So I'm still kind of confused here, because what we're going to want to do in the chemical case, what you're basically saying is, I want to take a subgraph and I want to replace it with another subgraph. Is that correct?
Yeah.
So that to me still sounds like a separate thing than just the base bond, adding bonds, adding atoms. If we don't want to make heads for those, we could just allow them to manipulate the structure. Like atom add would be append to molecule part 1. Bond add likewise.
But okay, append to is even more horrifying. Do you mean append or do you mean append to?
That's something we need to sort out.
Well, you could do either.
No, but you can't. It's not an L value. Molecular structure is in no way an L value.
Okay, I don't know what that is.
So you understand that you can't assign, if you take it and you append to it and you get another one of it, so to speak.
Mm-hmm.
You're not pushing back into some object.
Right. I would go with the traditional paradigm in Wolfram language that you get a copy back and you get a new thing.
Yeah, I think so. I think it'd be crazy to do anything other than that. But okay, this family of things one point we got to understand, this family of things is going to be about subgraph manipulation in the molecule. We don't yet completely understand this, but let's keep going because I want to see what the scope of the things we're dealing with. And I have no idea what molecule join is supposed to do. Is that just put two molecules just living in the same house type thing or what?
Yes. So they would be, just adding to, it would be one molecule with two disconnected structures.
Well, I don't, we need to be able to work with more than one molecule at a time in the same physical space, as it were. But I don't think we need to make an object that houses them together.
Well, so wait a minute. You're talking about the coordinate system that's defined. So once you do, if you can actually find the energy minimization thing to actually get the coordinates for the atoms, then the issue is if you've got, two water molecules sitting there or some cluster of 20 water molecules sitting there, you might want to specify the coordinates of each individual water molecule relative to its center of mass or relative to the center of mass of the whole cluster. And you're saying, how do you do that? Is that right?
No, I wasn't going there. What I was saying was you want to be able to measure things between two models of, two molecules. You want to be able to superimpose them, view them together in the same space, in the same graphics object in your notebook. But they still have their own independence from each other. Okay,
but take the case that I was talking about, because we need.
Is it a pure view thing?
To some extent, it's very much a pure view thing, but you also need to be able to do quantitative things between the two structures in the same space.
Well, when you say in the same space, you mean with atom coordinates that are absolute relative to each other.
Yes.
So embedding them in the same space. Okay.
Yeah.
Okay, but so take my example, okay, of the cluster of 20 water molecules.
Mm-hmm.
That is sort of another case of what you're talking about, or alternatively.
Yes, exactly. It is.
Okay.
It is.
All right. So, in a sense, what you're saying is that's when you say molecular structure or molecular model here, that would be, the question is what happens when you feed a molecular model molecular models, and how do you? Well, when we get to atom positions. What are they relative to? Are they relative to a center of mass, or what are the absolute atom positions?
Generally, they've just been absolute positions measured in angstroms, and they only become the absolute location in your coordinate frame only becomes important when you need to work with a second set from another molecule.
I get it. But okay, one trivial question: Did the world of SI impinge on this, and did it make it into nanometers, or is it always angstroms for the rest of time?
I think it's angstroms. It was when I moved out of chemistry 15 years ago.
Anybody, Michael or Jason?
No, in any software that I've encountered, you either put them in angstroms or Bohrs. Nanometers isn't really used for these.
Yeah, Bohr is only used for molecular orbital calculations, right, Jason?
What other kind of calculations are there? Sorry. Yes.
Empirical force field. Come on. Yes. Bohrs. I forgot about that one for Gaussian.
Okay. Angstroms is one of them that are formally allowed to be used with SI in the areas where they have been historically used.
In other words, the SI people gave up on trying to push that.
Yeah.
Okay, fair enough. Okay, but so we are going to standardize on angstroms. Is that the idea? Is that going to be the default if you give a naked number?
Yes. I would hope so, because yeah.
Okay, fine.
So traditionally in chemical data, we've plotted in picometers. We return values in picometers just because then your image size and your plot range are on the same order of magnitude. So hundreds.
What? Oh gosh, that's horrifying. Why did we choose picometers? That just seems crazy. I mean, why is picometers useful to anybody other than that you've got things in hundreds? Why do we care? I mean, why does that's having a pixel per? Is the concept a pixel per angstrom or something?
Pixel per picometer, furlong per fortnight.
Yeah, I can't speak to why it was chosen. I speculated that was the reason.
It seems crazy to me.
I think it was because it was SI, but the people who did it, I don't think are around anymore.
Right. Well, okay, but so is that something we can change, or is that going to mess everything up? But it's certainly something we can change if we change the name of the property of the atom positions property, right?
Right.
Okay, so that's a separate issue that we're going to have to address. Okay, but so now, okay, so we don't fully understand this business about. Okay, so the next question here is what happens when there are multiple. I mean, in your molecular model setup, there is nothing wrong with having multiple disconnected molecules sitting there, right? But
Absolutely.
There is no special representation for them. And when you do that, if you have molecules which all have a named site on them, how do you deal with the merging of those molecules with their named site? If they both have a named site called, X marks the spot or something, or, active site or something like the binding site, let's say, you have a molecule which has the word binding site, the name binding site for some position on the molecule, then you join that, cluster that with a molecule which has the same thing. How do you do it? You have to obviously rename them.
Yes, and we would probably do it very similarly to the way join across does with data sets or associations.
Okay, what happens with graphs, Roger? When you join two graphs, how do the vertices get renamed?
So there is I mean, that depends on which joining operation you use, first of all, because there are different ways of joining them.
Okay.
Okay.
Is there a graph join that just does a generic? No, there isn't. Okay. What are these?
Like a graph union, for instance, a graph intersection, and so on.
Okay. So graph intersection is not going to be problematic, but graph union, what does that do? Does that merge? What does that do to the vertex which is named the same in the two graphs? It probably merges it, right? So it just gives it the same. It gives it the union of the edges that vertex.
Open the details. See?
Yeah, I see. So that literally does do. So that never has a problem with two copies of the same thing.
No.
But in the case of molecules, we will have that problem.
Right.
In the case of
so what you want is sort of like a disjoint union.
Yes, but that has to, as Bob is saying, that there's got to be some renaming mechanism.
Yeah.
Mm-hmm.
Yeah. So
and
the other thing, even when you have that, there is always, like for graphs, there is always a canonical underlying thing called an index. Yeah. And that's managed by the system. So there's always an index associated with it has a name, the expression, whatever you used, and labels is the third thing, which is purely for display purposes.
Yeah. Okay. Fair enough. But what you're saying is, I mean, we haven't had to address the question of renaming. I mean, I know I've done this in graph rewrite type stuff of having to rename vertices in a graph. And for example, if you do a graph rewriting, yeah, I mean, anytime you do graph rewriting, you have to rename vertices. And the join across convention involves taking the names, and let's say you have two associations with names A and B. Don't you end up with a final association that has name list AB? Is that correct?
Something like that. It uses the name of one association, the left association.
No, I don't think it has to do that, right? The JSpec to contain missing elements when generated. So this is, by the way, somebody is making a lot of background noise again. But so
there's a key collision function there.
Yeah.
So it sort of delegates back to you.
Okay. So we would have to do a similar thing if we have some kind of molecular join.
Right, and also it kind of implies that the molecules themselves might have a name that could be used to disambiguate, C1 that's coming from both molecules, and we have not.
We haven't talked
about it. Yes, we have not tried to talk about names. It depends on your specific implementation of modeling system.
So Roger, in the case of system models, there you've got two resistors and they have different names, right? How are we handling that?
But when you instance it, you give it another name.
But what does that look like in terms of the design?
The class is like for resistors R, okay, in its own namespace.
So if we have a system model and it's a resistor with all of its various dotted names and so on, how do you specify the instance of the resistor?
Well, you get it back when you do this. You're gonna get an instance of it.
What function? When I do system model of that?
Well, it only happens when you. Well, that. No, I'm sorry. When you do system model, that's for querying. But if you're trying to put them together in a model to create a new model,
yep, then
you will get, an instance of it.
Okay, but what's the language level representation of that?
If you look at create system model or connect system model connect, then you see that you give the variables yourself.
System model connect. What?
You have to go to the source.
Is it in DocuTools?
Yeah.
By the way, we have a suggestion I'm noticing from somebody watching this Twitch stream about if there are multiple matches, if you're trying to do a match, it's a good point, that one wants to do pattern matching. It's not obvious. If you want to replace an active site, you've got a collection of molecules and you want to replace the active site by something else, there are two different things you might want to do. You might want to replace molecule 1's active site with something, or you might want to, as a pattern, replace all active sites in that cluster with something. Did that seem sensible, Bob?
Looking for the unmute button there. Yeah, that's very sensible. Right. There's the whole question of molecule patterns and working with them as well.
Roger, this doesn't seem to be.
No, it's there, but I just can't remember.
Does it not connect? What is the?
Hold on.
Okay.
So regarding names given to atoms or names given to sites, so I don't know how we would name a site in the molecule expression that we're working on. But
I see what you're saying. So what is a site? A site is not just a single atomic position, but it might be, for example, a I am so pathetic.
It's called Connect System Model Components.
Okay. What is its name again?
Connect System Model Components.
Okay, but I want to come back to this thing about naming. Okay, hold on. We're going to get to this in a second, but just let's talk about this issue. So you've got a radical or something. I don't even a group. Whatever. I'm so pathetic.
So call it a functional group, like a carboxyl group.
That's the name I was looking for. Right. Okay. So if you want to name a functional group, how do you do that?
Well, so what I would think would be substructure find, and then you do molecule, and then you have some representation of the functional group.
No, but I understand that. But the problem is within this thing, if I want to give a specific name to a whole functional group, how would I do that in this representation?
So I would make a property for the atoms, like so in a data packlet you have memberships, so where it belongs to this group.
Blah. Yeah. I mean, given that you're throwing in things like that chiral center, why not throw in some more annotation? I mean, that chiral center is basically collecting, random atoms and saying you're together now for some purpose.
Right. We would do the same thing for an active site, and you would define it by, you would name all of the atoms involved in that site. They don't need to be connected. and it's a very natural thing to do for a protein, for example.
Okay, but so what would be a generic name? Just like you have chiral center there, is there a generic name for a, special piece of a molecule where we could say this special piece is an active site and it involves the following atoms, for example?
Yes, something like that. And you can have more than one of them.
What's the right name for special piece?
You could call it functional group.
No, that's too narrow, and it generally implies that they're all connected, Jason. I think we need to come up with a name. Active site is too specific to proteins.
Molecular component or something. I don't know. Does
something
that
like that. We need to name a collection of atoms for whatever reason, whatever purpose the modeler has in mind.
I don't know. I guess, okay, I'll have to think about this. I guess I don't see the reason for that has to live inside the molecule.
Well, it seems convenient to me because that way we can generalize your chiral center notion to other kinds of random things that are needed for random purposes by other, for example, that might be, for example, I could imagine a case where, but maybe this is getting into a different thing, where some subpart of the molecule. Okay, so here's a question. Let's say you've got some fancy modeling system and it has managed to successfully position a bunch of atoms in the molecule, but other ones are hanging out unpositioned. Or for example, let's say there are some that are pretty much fixed in position and there are other ones that you're modeling, the vibration of, for example. I could imagine you wanting to pick up, it's basically just a way of naming. I mean, is there an analog of this in graphs, Roger?
Yeah, well, I was just getting to, there is a lot of ways to compute various subgraphs, okay? So we have a whole huge family. A lot of it comes from social network analysis, to find clans and cliques and so on. Yep. So there's a whole big group of those.
And they all return a list of vertices, which defines the subgraph, right?
They do.
Right, yeah, and we need something analogous here, and I'm just not sure what the name for it should be at this point.
Right, but wait a minute. Those are things that are coming out of a graph.
Right, they don't live inside the graph.
Annotations within the graph. Right, I mean, so given an annotation within the graph, one of those functions might be lazy in terms of computation and do very little, and just return the result of return that result. So okay, let's come back to your connect system model component. So what is this thing doing here? Do we have examples here?
Hold on, I need to look at your screen. Yes, you're looking at them.
Okay, but what does this do? What does it mean? How does it? But you're not showing identical things. You're showing things which already have unique names here. Right? So you're not addressing the issue that we were talking about, right? Where you've got a single resistor here. Correct?
Yes, but once you wire them up, that resistor, it still is going to be a unique, when it's wired into this model,
yep.
You want to be able to modify that resistor, and you can't modify the resistor that everybody else using.
Of course, right. So I'm asking you, how does it disambiguate the names as it puts two resistors into the circuit?
Okay, so you've already hold on, stop scrolling.
Yep.
Okay. The R and the L and the AC and the G, those are given by you. Those are names that you have chosen when you were a modeler there.
Fine. Okay, I see. But so this is saying R is an instance of
yes
resistor, that type.
Right. And if I needed two R's, I have to call them like R1 and R2.
No, I understand that. But when you connect the components, right? If both of them had a thing called R, what does it do? Does it give an error, or what does it do?
Yes. That would be an error, because you give them names here and you've given the same name twice.
Okay. Well, I mean, I think whatever the renaming mechanism is, I mean, one could imagine a situation in which it would be quite useful. I mean, if I was building some giant, I don't know, cascading amplifier-y thing, right, that had multiple stages, wouldn't it be really annoying to have to make up my own separate names at every stage?
That's why you use arrays of them. So yeah, there are ways to streamline that when you're going to use many of them.
What does an array of those look like? Instead of is it a set of string names, or is it something different?
Well, you just declare it to be an array of a certain length. So then every part of it is indexed like an array. So R square bracket 1, R square bracket 2, and so on.
Oh God. Okay. Yeah. I mean, that's right. It's a little bit. I mean, that's not okay. So we have not really addressed this question of overlaying graph. I mean, this is the nasty underside to everything to do with graphs, is this whole naming business.
No, it's not really. No.
What do you mean? I think it's.
I mean, you have a problem in language design why you have avoided it, but no, it's not really a problem in graphs.
Well, what do you mean it's not a problem? You've got to have an actual name. That's the way you refer to the vertex.
Yeah.
So the fact that the name is arbitrary and the name has to be rejiggered when you merge two graphs seems, is there an elegant way to do that?
How to automatically generate new names.
Right. Well, so I mean, one obvious way to do it is to simply take the implicit, if you have a list of graphs, you take the implicit index of the whole graph, which is the, sequence number of the graph in the sequence of graphs you're giving, together with the index number of each vertex, and you start having, conveniently, obviously, we can have arbitrary expressions as the names of our vertices. So we can say, 1,7 and things means vertex 7 of graph 1 and things like that. But it hardly seems beautiful.
No.
Is there a better scheme?
For graphs, there will always be an index underlying that, and that's always an integer, and it's always sort of starting 1, going to.
Wait a minute. Who's for our graphs or for graphs in the world?
No, for our graphs.
Yeah, okay.
And that's implicitly sort of in the world as well, but it depends on what kind of presentation.
If it turns out to be true that the whole universe and space-time is a graph, it will be almost comical. I mean, that's the case. One of the reasons that's hard to get one's head around.
Stephen, there are all kinds of things going on. I know 150 potential graph languages or graph domains of applications. Yes, they all have their own little things going on.
What do you mean? But does anybody have a clean solution? This particular issue of merging two graphs and renaming things, is there any? I would have thought that over the years we would actually by now know all possible solutions to that, and I think I know a few, and none of them are very nice. So I'm asking: is there some brilliant, innovative solution to that that I'm not aware of, or are they all kind of yucky solutions?
But see, I think the problem is that you kind of want to have the cake and eat it too. So, and so depending on what your goal is, there might be some that look great and some that don't look so great. Sometimes you want to be able to infer where they came from.
Yeah, right. And sometimes you don't care, right? So you might want an operation that's similar to flatten, because like in flatten, what you're doing is, let's say you've got, in flatten, you can either know, with your whatever it is, a thing like this, right? You either know where everything came from and everything has its position, or you can go ahead and say flatten it, in which case you have the content, but you don't know the provenance in the same way. And I could imagine the same thing for graph labels, names of vertices and graphs, that you have an operation like a graph flatten type operation that will simply take all of do something similar to this, right? Because this started by having, in this case, the elements here are, the 221 element here. But in this case, that's been flattened to just a single index. Does that make sense?
Yeah.
That seems like do we have such an operation for relabeling, renaming, renumbering the vertices in a graph?
Yeah, effectively.
What is it?
No, it will give so the flatten has just, from 0 to 8, from 1 to 8 as an index, right?
Yes.
And then the former one has a vector position.
Exactly.
Okay.
Which is exactly what we're talking about here for graph merging, graph joining. Go ahead. Yes.
And actually, you put in a function, which I've written so many times, which is called mixed base or whatever it's called.
Mixed radix?
Mixed radix. So you can if you knew the original structure, you can easily reconstruct.
Right. Right.
I mean, it doesn't look at them when you look at that, but you.
No, I understand, but it's a thing for doing. It's what Fortran used to do, or whatever. It's the thing for unrolling arrays into flattened things.
Right.
Okay. So, all right. So that's a separate issue, and that we should talk. I mean, that's a separate thing that we should have on the agenda. Is some kind of graph relabeling, graph flattening. I mean, it's an interesting question whether we can actually have graph operations operate on these molecular model constructs.
I think there's a lot of analogy there. And
yeah, but the question is, can we actually get away with using the same namespace?
Like, could we use vertex add and edge add on a molecule?
Yeah.
Yeah,
That's
I mean,
that
would be the easy.
Right, but the way vertex add works, remember, is vertex add is labeling the vertex by giving its vertex name, right? By giving the name of the vertex. But we don't have, other than the, vertex add, other than the, okay, so vertex add makes the graph by adding the vertex to the graph G, okay? The problem here, and then we'd have edge add as well. But what you'd have to do here is right. Add
and that's too low a level to do for molecules.
Yeah, they are here, by the way, because this is also, they are here because you might have sort of in a loop where you incrementally construct a graph. That's why there is a system like that.
Yeah.
Right, you know, which is rare for a molecule. Is that correct? Despite your nested way of constructing an alkane here.
Right, but I just wouldn't see a reason not to allow low-level manipulation.
I think
no, but you can always do it by taking the thing out of the molecular out of the molecular model and just manipulating it, right? Because it is just an expression structure.
Right, you could just append.
But will this actually work? Because yeah, this would work. I mean, edge add. I don't see why you shouldn't allow edge add and vertex add to work on this molecular model. But we need to keep going and just take a look here at some of the other things. So this is
the other thing, though, Stephen, is you have to worry about 3D coordinates versus 2D coordinates versus any coordinates at all. And inherently, graphs don't have positions for the vertices until you embed them or do a layout. Whereas most people, at least, okay, one world of modelers don't rely on it. The other half of the modelers do rely on three-dimensional atomic positions.
Look, when you put in a smile string that nobody's ever seen before, you don't know the positions.
Right, and generally you don't care. But at some point you might want to put that into three-dimensional space, and from that point on, everything you do with that molecule, you will expect 3D positions to go along with it. And if you're adding an atom to it, you need to include a position.
Oh, you need to include a position for the atom,
or
so
be able
optionally,
or be able to compute it from how you attach it by the.
Okay, but are we imagining then that in this thing that is turning into potentially a pretty big association or a pretty big collection of things in entity instance, that the actual positions might be listed here in the vertex list?
Well, Jason and I have been keeping them in a separate list that's named. Rather than keeping each
as an option to the
why do that? I mean, why not? Because in this case where you want partial, you know, for example, if you want partial locking, you know, of positions, right? It would be more convenient to annotate some of these with their position and leave the other ones undetermined, than to start messing around trying to say, oh, you know, index number 17 has a position, but index number 18 doesn't have a position.
Yeah, if we go that route, I agree. Putting them with the atoms is probably the better way to go. And then
so I would see
being locked or not locked.
But do we have any mechanism? Sorry, in graphs, Roger, do we have any mechanism to give the embedding coordinates?
Yeah, not with the. Actually, you can.
So you can do it with property, right? You could do it with property and say vertex position or some such other thing. Is that not correct?
That's it. Yeah, that's it.
Okay.
But if you want to use the wrapper style, you know, in line, yes, property is it.
Right, but that will work. Just as so in this case, you know, it might be convenient to annotate the you know, atom list, or it might be convenient to have a separate annotation, you know, a separate thing. So maybe both of those could be considered, although we have to decide what the canonical form is and whether the canonical form involves annotated positions, which I have to say seems to me to make quite a bit of sense. Do you ever have to annotate bonds with something that has been computed about them? Isn't that how your whole, I mean, in the world of orbitals and things, isn't there just a ton of annotation that you might have to give?
In my experience, we haven't worried about annotating bonds other than the bond order, the bond type.
Okay.
What about you, Jason?
Well, I mean, so in the underlying library, the way that chirality is handled is either through an atom annotation or a bond annotation, but it's kind of ugly, and so we need to process that before exposing
but that's,
it.
Okay, I don't care about that. But let's have a quick look through, because we're about to run out of time here. So these are now properties of the molecular model.
Right. And there will be on the order of 100 or more of these things that you could compute. But then, so then there's the question of what about when you can give options to them, like that smile. So there are many options that you can give for a smiles, but I don't know of any examples in the language where you have an object and you give it a string argument to get back a property.
Well, those are like property attributes, right? I mean, they're like what date that population was measured for and things, I think.
Okay, so when you query an entity just as a head, like calling entity value under the hood, you can give it options like that. Is that correct,
Michael? Is that the way this works there?
More or less.
I mean, there it would be more like a property entity.
I mean, it would be like it would be more in the spirit if there would be an additional header on both, rather than linearized.
Yes, I understand. So there's another concern here, which is that these atom positions are hardly, to not mix too many metaphors, set in stone, so to speak, in the sense that these are, these will typically be the output of some random molecular modeling program, right?
Right, and we want to give them the option of making more. You can, I mean, I've got a function in there called embed molecule.
But sometimes are they centralized somehow? Like the center of mass is in the 0, the origin, or what's the?
I think usually, yeah.
Okay.
Is it actually the center of mass, or is it simply the average of the coordinate positions is 0, which is a very different thing, because there might be a uranium atom somewhere.
Yep.
I'm not certain.
Okay, what should it be? I mean, particularly if we want to be able to do computations that involve...
Compute the mean for those guys and see what it says.
Yeah, fine. Not 0. That molecule is in weird motion of some kind.
Well, I don't know if I would call it motion. I mean, it's just in a different place in space, that's all.
Yeah. Okay, but okay. But we do need to standardize that. And but for example, when you want to look at molecular, vibrations and things, doesn't it matter that you've got that thing doesn't it matter that you know where the central mass is?
No.
Yeah. Well, so when you do vibrations,
somebody said yes, somebody said no. What? I mean,
translation invariance is
no. So when you do molecular vibrations, you actually filter out those coordinates. You do a coordinate transformation, and you take 6 coordinates out, and so you only.
I see.
Work in internal coordinates usually, but then you have to project back, and you have to know where things are when you project back.
Is this for calculating the actual physical vibrations of the atoms in space, or just the frequencies?
I would have thought the physical vibrations in space.
Okay, so like you wanted to do an animation or something like that. Or
right. So you're right. Obviously,
molecular dynamics.
Right. Okay. Let's keep looking just forwards here. We've clearly got a lot more to do here.
Yep.
Adding coordinates. What is this? Okay. What is this? Embed the molecule. So this is actually doing molecular structure computation. Is that correct?
Right. So it uses it computes a distance bounds matrix where atoms that are 2 or 3 bonds away from each other need to be within a certain distance of each other. Tries to generate random coordinates to fulfill that matrix, and then uses some cleanup code to try and make it into a more reasonable structure.
Just to understand, so we got a lot of random functions running around here. I mean, how successful can this be? If I give you a random 100-atom molecule, and I've given you roughly the right structure, can you actually evolve it to something that is a pretty accurate molecular structure using this?
So if you give us 3D coordinates to start with that are not bad, then we can go on to the second thing, which is optimizing via force field. and come up with something that is pretty good.
So let me understand what not
so,
bad.
I mean, just as a name, don't call it optimized geometry.
Okay.
Yeah, hopeless, right? Yeah, that will be. That's
just at least give a sense that it's related to molecules.
right.
Right.
Yeah.
I mean, none of that is going to that will not survive. I don't know what it should be called, but that's not it.
Okay, Stephen, for your example, though, 100 random molecules, and it depends on how they're connected. If it was one big long chain with no branching, it would be hard to do with the distance geometry approach. But if it was a structure that had rings and things like that and branching, then it wouldn't be that hard. Again, hardness is somewhat subjective.
Okay, but given a smile string, doesn't the smile string contain some information on the geometry?
No, just the connectivity.
Just the connectivity. And the more connectivity you have, of course, the more rigid the structure becomes, and the much easier it is for distance geometry to do its job.
So in the case of okay, but so our graph layout, for example, if you just apply our graph layout to the implied connectivity from a smile string, does it produce something that is vaguely like a molecule or hopelessly? I mean, is there a version of graph embedding?
Generally hopeless, because for molecular structures, a 6-membered ring you expect to look like a hexagon.
And there are preferred
Roger,
bond angles
here's
that
a
are.
Question. Yeah, I understand. So here's a question: do we have a version of graph layout that forces the typical distance between nodes to be the same? In other words, graph layout has some vague, spring type reason to keep.
So there are many different algorithms.
Of course.
One general one is called spring electrical.
Indeed, which has that general approach, right? It tries to keep things roughly the same length.
Mm-hmm.
Yes, you have a
spring and an electrical repulsion.
Yep.
And you can get something reasonable with spring electrical embedding if you add in dummy atoms before embedding and then remove them, so that forces two atoms to have a 120-degree angle in between them because you add this dummy atom, third atom.
So in other words, you take something like the valence of the thing and you add dummy atoms to go to the valence to force these angles or something, or what?
Right.
But so having something which does a first cut of what the molecular structure, so that sounds like a reasonable procedure, not totally ridiculous algorithm for getting a first cut for what the structure is. Is that true?
Well, that's a 2D structure.
I see. Why can't you do the same thing in 3D?
Spring electrical works in NAD.
Right.
But why would you want to do this? Jason has external programs that do the great job.
Good.
Well, wait a second. But Bob was just explaining that if I give you a 100ane is called, a big long chain of stuff, right? Then it just won't work, right? You're saying that if
distance geometry would have a hard time. If I could perceive that was just a chain, I could use an algorithm to generate the positions with no trouble at all, completely.
Well, except that if I might say so, a chain is going to be like a snake. It's going to, knowing what its sort of optimal, I don't know. I have no idea what an actual, it's like you got a giant polymer molecule. It doesn't actually.
Right. It's very floppy and flexible. Right. It is. But what you want to do is avoid self-crossing paths, if you will, through space.
But what's the right answer for a random long polymer?
Yeah, that's a very reasonable thing to build. And then if you wanted something with some more rigid or more refined structure, then you could say I want it fully extended, or I want.
Okay, so this leads to another problem. So the other problem is there isn't a unique answer, right?
That's right.
Right. It's a hard problem embedding large molecules.
Yeah.
Well, I realize that, but I'm saying it's not even clear what the, unlike for some of these other purposes where there is an energy minimum and all this kind of thing. In the case of the big, long, snaky, polymer, it's a very flat landscape, isn't it?
It is. It is. It's a very large catchment region with a lot of little dimples at the bottom that are very shallow. And, any one is not very different from any other one. So, we could easily generate something that would satisfy most people. And if it doesn't, then they have the opportunity to refine it or to try to generate another one.
So what you're saying is, ab initio, we can do a somewhat reasonable job given this, given the connectivity data, given the bond connectivity data, not just given the bag of atoms. You've got to have bond connectivity data.
Yes.
Not ab initio.
Wait. Who's saying ab? I mean, ab initio might mean just with the atoms, and I'm saying forget that. You got to have bonds.
No,
but are you saying
ab initio means kind of you write down the Schrödinger equation?
Yeah,
that's the current.
Okay, I understand that. That's what ab initio means for the But I'm saying ab graph. I don't know what the Latin for graph is, but from the graph, from the connectivity graph, right? So. Which has assumed some kind of bizarre symbolic representation of the molecule in terms of bonds, which I don't even know whether, I mean, presumably there are molecules where it's hard to even know what you mean by a bond, or is that not the case? Is chemistry so...
No, there are exotics.
Yes, there are some situations where, a 3-center 2-electron bond has been postulated to be the appropriate representation. But we're not trying to deal with those.
Well, wait. Before you glide over that with extreme speed, okay? A 3-electron, 2...
No, 3-center 2-electron, 3 atoms.
Okay, so this is like we don't have a graph, we have some kind of hypergraphy type thing.
Exactly. And it's because the molecule is what's called fluxional, and sometimes the bond's here and sometimes it's there. They're going back and forth between 2 different atoms.
Right. Well, that's life in quantum mechanics.
Exactly.
Okay. So basically, the whole thing is fundamentally, the idea of bonds is kind of a classical fake.
It is.
You're saying... not really. No, actually, that's not quite true.
Okay. Explain, Michael.
They typically... there's quite a bit of literature on the subject. Boulay and others, Primož. It's basically an effect of the interaction with the infrared sector that collapses this down.
So you mean there is an effector measurement going on because because of the interaction with what? Effectively with radiation?
Yeah, exactly. With the infrared radiation from QED.
Okay, that's an interesting claim. So the claim is that a molecule in a heat bath is fundamentally a semi-classical system because it is continually being measured by the heat bath. Is that what you're saying?
That's a little bit stronger, but yeah, in this direction. I mean, you don't need heat baths. I mean, the vacuum will do.
Oh, but
that's the whole point. Like, if you have a couple of atoms, it doesn't flow apart. Not even the center of mass flows apart, because it's permanently measured with the infrared vacuum photons. I think that's the modern viewpoint on this.
I see. So what you're saying is, so the question is, why does a hydrogen molecule not have an uncertainty in its size that grows with time? Is that the question?
Exactly.
Oh, that's a nasty. I've never thought about that before. And so your claim is that, what do the chemists here say about that? Have they ever thought about that before?
I just like to think that there's an increased density of electron between the 2 protons that draws them towards the center of mass.
That's not addressing thinking about the Schrödinger effect in that situation.
I don't know. The philosophy that comes up between you and Michael in these meetings is sometimes I don't know what to contribute to it.
Okay.
And of course, my model is rods and tubes in a Dryden model, and they're fixed, permanent, they'll last forever. They're stainless steel, they don't rust.
Right. Okay. But fair enough. But seriously, as we think about building this for the future, what you're saying is that we could imagine a time in which it will be relevant to have a hypergraph as part of the molecular model.
I think we could go in that direction, yes.
And is that the way we're constructing it right now with this notion of bonds and these special pieces, whatever we're calling them,
ensembles? Would ensemble be appropriate?
I still like hyperedge. I mean, it's some relationship between multiple vertices.
Oh yeah, but it smacks too much of graph theory.
Yes, and hyperedge is. I mean, but you're talking about the thing for chiral centers and so on. Yes, and the thing for binding.
I like ensemble. It has a provenance within chemistry itself already.
Really? For that?
Yes. Well, not
that,
typically that, but an ensemble is a group of atoms or a group of molecules.
It's not a group of states like in the canonical ensemble of statistical mechanics?
That's how I know it.
It's there also. It's used there also.
What about things like, well, I guess clusters means of whole molecules and things.
Clusters could also be monatomic atoms or monatomic molecules in a cluster. Also, like neon atoms.
Right. So I mean, yeah.
Together by Van der Waals forces, but.
Okay, but let's see. Zoom, looping back for a second, and we really have to wrap this up.
Yeah.
Because what we will have to continue this soon, but okay. Back to this thing about, so we believe that we will be able to have reasonable functions that take a connectivity specified molecule and actually refine the atomic positions in that molecule. Is that correct?
There is up to a limit to a certain size of molecule, or there will be molecules where we will fail.
Yeah, so we won't succeed in proteins because that requires special purpose computers and all that. And only one person I know has actually claims to have succeeded in doing that in a reasonable way. But what?
And if we want to take a linear chain of 80 carbon atoms and create a structure of it, then we're going to have to work to make some new function to do that, because right now the library will fail at something so fluffy.
What do people actually care about for this? Okay, give me a sense. Are we talking 100 atoms? Is that the size of molecule that we can deal with, or what?
No, I think we can go larger than that.
How large?
Several hundred, because there are drug molecules that are that large when you include hydrogens. I think we can go that large. I don't think we need to worry about the de novo structure generation from a smile string for them. I think we can use a combination of rules, heuristics, and distance geometry to tackle that problem and probably do better than RDK distance geometry alone.
Okay, so wait a second. So give me a sense. Let's say you've got a 200 atom molecule and it's grinding on a CPU. How much CPU time does it take to come up with a reasonable solution?
If you use heuristics, you can do it in a few seconds.
Okay. And do you get something better if you're prepared to grind for hours?
Yes, depending on what the method is. If you want to use a force field calculation, it might not necessarily be for hours.
And so when you do this, I mean, when I've seen actual sort of simulations of molecules doing their thing with, binding sites and so on, the molecule, and even in like the touch press app about molecules where you can kind of, where Theo simulated them and got it so that you can, use your fingers on an iPad to move the molecule around. There's a high degree of floppiness in these molecules. And I mean, how do we represent that here? So we've got atomic positions, but can we represent, actually, I wonder how Theo represented that for that app. Does anybody know?
No, I don't.
It'd be interesting to find out. Jason, do you know that?
So representing no, I've not seen the app, but representing the floppiness.
I've seen the app.
There is the concept of flexible bonds or rotatable bonds in a molecule. And
okay, but guys, Jason, I can't believe you have not seen this app. This is the app that Theo made for Touch Press maybe 3 years ago or something, where he did a whole bunch of computational chemistry to work out for a bunch of molecules to work it out so that you can literally put your fingers on an iPad screen and be moving atoms around. If you haven't seen it, you should definitely get it and play with it. But the question we can ask Theo is, how did he represent molecules? Because that will be a really useful thing for us to have. If we're bothering to do all these computations, let's represent the molecule in such a way that you could, in some VR system or something like that, actually do the same thing that was done in that app and let people pick up atoms and move them around and so on. You see what I'm saying? And have the molecule actually realistically flop around. Right. I think given that we're going to the trouble of computing all this stuff, we should be able to compute, I suspect, what you need to compute are derivatives of positions as well as positions.
Yep. I've got code for all of that, up to second derivatives.
Okay. And you think that will represent, I mean, because that app, you can see I'm so bad at chemistry. The actual little rotatable pieces actually rotating all the way around.
It sounds like he's doing some kind of molecular dynamics You know, using
yes,
Newton's laws of motion along with a
but
force
he
field.
pre-computed. The whole point is what he did was he pre-computed that, because you don't get to run that in real time with your fingers on 10 positions on an iPad, right? So what he's got is a pre-computed representation of the molecule, of the molecular structure.
And you can interact with it. You can push it.
You guys are so, I can't believe you guys don't know this. This is
I've heard about it, I just have not seen it.
Well, you should see it. I'm going to try it now. I've got this big iPad Pro sitting on my desk. I've not tried it on that, so I should be as embarrassed as the rest of you for not having tried it on that thing, because
if you can push it and just make the whole thing spin and its internal motions continue.
No. Every atom moves around looking like it's on a bunch of springs and things.
Okay.
And the atoms do not collide with each other. So there's some, it doesn't just, it's not just
There's a YouTube video.
Okay. I'm sure Teo has promotion for it. Okay. All right. We need to all go to a quite separate and different meeting.
Right.
This we can watch. We can skip the.
If you clip into the half of it, you'll see the wobbling molecule. There you go.
Okay. That's not really doing it. Well, more or less doing it justice.
So it's. I mean, you're looking at the results of an MD simulation.
No. I know, but the whole point is that you can do that interactively. You can move that around. That's the point. That's the non-trivial part, and that's why I'm asking you about doing that. Okay, we got to wrap up here. So if I don't know whether anybody's been watching this, but if you have, I hope you had an interesting time, and there'll be another one of these, and maybe if we get good feedback about this as a Twitch event, we will live stream the next episode. And anyway, at least for me, it's a great way to learn something about chemistry. All right. Talk to everybody in due course.